Good morning, everyone. So, shall we wait for some more time so that others can also join? Piyush, shall we start?
Hello. Yeah. Am I audible?
Yes.
Yeah. Okay. Thank you. So, hello everyone. Good morning. Okay. So, how many of you have watched week 5 content? At least first two lecture. Please raise your hands. Okay. Great. Okay. So, today we are going to discuss about functional dependency and how to calculate candidate key. Okay. So, okay. Let me present my screen. Is it visible?
Yes.
Yeah. Okay. So, first we will start with the functional dependency. First, we'll start with functional dependency. Then we'll discuss about candidate key and how to find a candidate key. And then we'll discuss about lossless decomposition. Okay. And after that, we'll take few examples on Mentimeter. Okay. So let's start first with the functional dependency now. Okay. So suppose R be any relation schema. And if you are saying that alpha determines beta, it means that alpha and beta are the subset of attributes of relation R. Okay, so how to read this alpha arrow beta? So basically, if alpha uniquely determines beta, means beta is dependent on alpha, right? Now, what this alpha uniquely determines beta means? Okay, say for example, there are two attributes A and B. Okay, and A having A1, B having B1, A2, B2. Now, if we add one more tuple here, that is A1, then it must be equal to this B1, that is B1. Okay, so A1 must uniquely determines B1 only, that is alpha here and here beta here. Okay, so if we say A1 and here B2, then this functional dependency, that is A determines B, does not holds true here, because A1 is also determining B1 and here A1 is also determining B2. Okay, so functional dependency A determine B does not holds true here. Okay, so similarly, I have taken the same slide from the our weekly videos. Okay, so for basic condition is to check that T1 alpha equals to T2 alpha. So please note one thing, alpha or beta may be an attribute or a set of attribute here. Okay, now we'll discuss. See, suppose here a roll number. Okay, so first we'll discuss about roll number determine name. Okay, now we'll check for this functional dependency. Now roll number must uniquely determine name now. Okay, so say suppose here roll number 5001 is determining Ramesh. Okay, now can you see any other roll number with the same roll number here? No. If you see here roll number 5003, that is Rakesh, and roll number 5003 is also Rakesh. So our this functional dependency holds true here for this table. Okay, now see here there is not it is not necessary that you have to consider this T1 and T2 in the sequence only. No, you can consider this as T1 and T2. So basically, if you are taking alpha and beta, so you can take any two tuple from the given tuples. Okay, now
Sir, we
yes,
have one query here. Can we ask?
Yes.
Yeah. Can we talk this attribute right now? We are talking. Suppose the roll number is one attribute and name is another attribute.
Okay.
So can we talk one and many one type of thing between attribute? So it will be easier to understand like that. Like alpha tends to beta. So as the gap has sent wrote in the message, so can we say that it is 1 between the two attribute? I'm defining the new. I'm defining the new way. The new 1 or many one.
Yeah, I get your point. Yeah.
So it will be easier to understand and visualize.
Right. So alpha uniquely determines beta. It means alpha must there must be one-on-one mapping between alpha and beta.
So right. It must be 1.
Yeah.
Okay.
So see, suppose here a roll number.
Can I interrupt a bit?
Yes.
Can you check this equation? It is T1 alpha equal to T1 beta, I think.
T1 alpha equals to T2 beta.
T1 beta, that T2 alpha equal to T2 beta, no?
And
Yeah,
alpha
here
beta
this is
are-
T1 and this is T2 and this is
Yeah.
alpha and this is beta. So T1 alpha equals to T2 alpha, right? Now if this condition holds true, then we have to check for this condition. That is T1 beta, it must be equals to T2 beta.
Okay.
Yeah. So Piyush, I want to interrupt once. Okay, what you said about A1, B1, A2, B2, A1, B2, right? There is something slightly different about it. That it's A1 determines B1, A2 determines B2. The thing is, A1 can determine anything else, but B2 cannot be determined by anything else. That is what it means. Bhaskar, is that correct? Is Bhaskar is there?
Yeah. So, hello, am I audible?
Yeah, you are audible.
Yeah. So, if A1 is there, then it should be that same thing. That's the
B1,
whatever.
right?
Yeah. If A1 is repeating, then A1 should have the same value.
Same value, that is B.
Yeah,
Okay.
it's correct.
Okay,
Yeah.
okay, got it. Okay, we are also self-controlled. Okay, thanks, Piyush. You can carry
Okay.
on.
Now let us discuss for another functional dependency, that is roll number determined course. Okay, now same here you can see roll number is 503 and here beta is DBMS and here roll number 503 and here beta is Java. Okay, so this is alpha and this is beta, suppose. Okay, now this functional dependency does not hold true here because roll number 5003 is determining DBMS also and it's also determining Java. Okay, so this functional dependency does not hold true. Now let us take a combination of, say, roll number, name determines course. So in this case also, now this combined is alpha, okay, and this is beta. Now this 5003 Rakesh determining DBMS also and 5003 Rakesh is determining Java also. So this functional dependency does not hold true here. Now let us add one column here, say department. Okay, I am focusing on these two tuples only. Okay, because rest of the tuple is uniquely determining each attribute. Okay, so now here I am adding. Okay, so DBMS belongs to IT department. Say suppose IT department and Java belongs to CS department. Okay, now if you see the functional dependency of course determine department for these two tuple only, then DBMS belongs to IT department and determining IT department and Java belongs to CS department. So now this functional dependency holds true here. Now instead of Java, if I make it DBMS, then this functional dependency will not hold true. Okay. Any question?
Sir, I'm having a doubt.
Yes.
Sir, here roll number is mapped to name. As
Roll
we said
number
that,
is mapped to name. Okay.
Name. Is it necessary to check the combination as well? As you said, roll and name, the combination considered to be alpha is mapped to course. So in a table, is this discussion related to particular two attributes or the combination of attributes is also to be considered for this concept to get valid?
Now we have to see all the combination of attribute also. Basically, this is the only concept that it must satisfy this functional dependency.
No, right
okay?
now in this table, if only roll number and name satisfies this condition, is sufficient, or a roll number and name combination must satisfy this condition with course as well, and roll number with name and course as well? Is this all possibilities we need to consider or not?
Yeah. There are some different rules of this functional dependency. We'll go through in the next slide. Okay. From that we can determine. So suppose here roll number is determining name and name is also determining course. So automatically this roll number will determining course. Okay. So suppose instead of Java, it is DBMS only. Okay. Now this functional dependency holds true here. That is roll number, name, and name determine course also. Now, both the functional dependency holds true. Now if you see this Armstrong axionym, by using this transitivity rule, we can say that alpha determines beta, beta determines alpha,
Yes,
then alpha determines gamma also. Similar rule can be applied here. This is roll number determining name, and name is determining course. Similarly, we can say that the roll number is determining course. Okay.
Yes, sir, got it. Thank you,
Yeah.
sir.
Sir, can you explain the last point you talked about, department IT and CS?
Department IT and CS. Okay. Okay. So suppose we add one more column here, say department, and DBMS belongs to IT department and Java belongs to CS department. Now, if we check this particular functional dependency, that is course determined department. Now, it must be unique. For DBMS, it is determining from IT, and for Java, it is CS. So, this functional dependency holds true here because DBMS is uniquely determining IT department and Java is also uniquely determining CS department. Now, suppose instead of Java, I put DBMS here. Now, this functional dependency will not hold true because DBMS belongs to IT department also and DBMS belongs to CS department also. So, according to this functional dependency, this does not hold true. Okay.
Okay. Thank you, sir.
Yeah, I have kept some examples. After that, we'll discuss those examples. Okay. Don't worry. Yeah. Now there are some different rules for functional dependency.
Sir, can I ask one thing before
Yes,
going
yes.
further? Can you write the three condition and can you make the clear one idea? I have a three condition. When
Okay.
for the same alpha, there is a unique beta. For
Okay.
unique alpha, there is a unique beta. Condition one. Second one, for the two alpha, there is a one beta.
Okay.
The two alpha value. Yeah.
Okay, 1 minute. A1, B1. That is A1, B1. Okay. Now
A2, B1. Yeah. And
A2,
third
B1. Okay. Now
no. So the second condition is that for the two different value of alpha, same beta. Third condition is for the same alpha, 2 beta.
same alpha, 2 beta means for this A2, B2 also, right?
Yeah, I
Yeah.
think he's asking means in different scenarios. So
Yeah.
So in these three conditions, can you tell me the where the dependency hold and where dependency not?
Okay. So we'll discuss it here. Okay, say it is A and it is B. A1 is having A1, B1 and A2. Sorry, A1, B1. This is our first. Now second is A, B, A1, B1, A1, B2. Second. Now third, A, B. Now A1, B1, A2, B1. Now say suppose fourth condition A, B, A1, B1, A2, B2. So this is you want to, right?
Yeah, yes, sir. 3 and first is same, I think.
A1, B1. This is A1, and here it is A2.
Okay. So first one is meaningless because tuple is the entire same, no?
Yeah. If you see the functional dependency, A determines B here. So if you see our previous slide, if you take it as T1 and T2, so T1 alpha equals to T2 alpha. Here also T1 beta equals to T2 beta. So T1 is uniquely determining B1. So A1 is uniquely determining B1. So this functional dependency holds true here.
Okay. But one thing, sir, whenever we talk about the theoretical table, we don't talk about the duplicate of the tuple, no?
Don't talk about duplicate.
No, Kumar, there could be another C also here, tuple, which could be different, right?
Okay.
There could be another attribute C, which could be different. We are just comparing the relation between A and B, but it's not like there are only two tuples A and B.
No, my meaning was that T1 and T2 was look the same tuple.
Yeah, it looks same because we are only comparing AB, but there may be a more that attributes, right?
Yes.
Which are different. There can be a C, which
here you can see three attributes are there. If you consider only roll number and name, so these two are same thing. Okay. But there is one more column here that is code. It is having DBMS and Java. Okay. Yeah. Now the second condition, A1 is determining B1 and A1 is determining B2. So in this case, this functional dependency does not hold true here because A1 is determining B1 also and B2 also. Now here A1 is determining B1 and A2 is also determining B1. So here this functional dependency holds true because we are looking at A1, that is alpha here, because A1 is uniquely determining B1 and A2 is also uniquely determining B1. But in this case, B determines A is not holds true here. Okay.
Okay, clear.
And in this fourth case, it's A1 B1 and A2 B2. Here also the functional dependency holds true. Okay. And here B determine A is also holds true here. Okay.
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 In general, we can say that in attribute one to many not hold true, except everything holds true.
One to many, yeah.
Second
Yeah.
condition look like one to many.
Second, yeah, one too many, yeah. Right.
Okay, sir.
Piyush sir, can I interrupt in between?
Yes.
Yeah. So just one question I want to ask. So can you all raise your hand who all have learned about functions, relations? I think you all know about these things. Mathematical functions. What is the definition of a function? Please raise your hand. So all of you have learned about functions. So what are the three conditions that a function must satisfy to be a function from a relation? Can anyone tell me?
Okay, we can tell like example wise, sir, for the same value of x, there should not be two value of y.
What do you Bas, that's what I want. Only that condition is what I want. Other two conditions is not relevant over here. So what is the topic that we are learning today? It's functional dependency, right?
Okay.
The first word is function. So it's just same thing. Just compare it with the mathematical function. If you have in the domain a value of x, it should uniquely map to one value in the range. That's
1
it.
to 1. That's 1 to 1, sir.
Okay, yeah.
So A is the x and B is equal to y.
1 to 1 is okay. Many to 1 is also okay, but you cannot have 1 to many.
1 to many, yes.
Yeah. So that is the definition of function, normal mathematical function, and here also it is same. Yeah. Okay. Continue, please, sir. Please.
Yeah. Okay. Thank you, Pastor. Yeah. So, the important point to note here that if A is determining B, it does not mean that reverse is true. That is B determining A. Okay. So as you can see here, A determines B, but B is not determining A. Okay. So this condition does not hold. So this rule is does not applicable here. Now let us see about Armstrong experiments. The first rule is reflexivity. So if beta is a subset of alpha, then alpha determines beta. Now what is argumentation? If alpha determines beta, then gamma alpha equals to gamma beta. Okay. Now according to transitivity, if alpha determines beta and beta determines gamma, then automatically alpha will determine gamma here. Okay. Now based on these three rules, we have derived some more rules. Okay. That is additional rules.
The
Sir,
gamma.
can you please explain?
Okay, 1 minute. Okay, yeah. See, okay. Which rule? All the three rules?
Augmented.
Sir, the first one.
Reflexivity. Okay.
Reflexivity also. With example, sir.
With example. Okay. So basically, say there are three tuples. That is A, B, and C. Okay. Now, if AB is determining B A. So B is basically it is a subset of alpha. Okay, this is alpha and this is beta. Okay. Now B is a subset of alpha, right? So we call it as trivial function dependency here. Now for augmentation, say A determines B. Now we can say that AC also determines BC here. Okay. Now similarly for transitive, we already discussed that A is determined B and B determines C, then we can say that A determines C. Okay. Now there are some additional derived rules. Is union. Okay. If alpha determine beta holds and gamma determine and alpha determine gamma holds, then alpha determines beta gamma also. Okay. However, in decomposition, similar thing. If alpha is determining beta and gamma, then alpha is determining beta also, and it determines gamma also. Okay. Same for pseudo transitivity. Here, let us take one example. Say, suppose we have functional dependency. Say A determine B, B determine C, say D determine E. Okay. Now, if we take the closure of this functional dependency, Now, by using these rules, we have to calculate the closure of functional dependency. That is, A determine B, here B determine C. Now, by using this transitivity rule, we can also say that A determines C. So A determine C. Now here, by using decomposition rule, we can say that D determine E and D determine F also. So I'm writing it here, D determine E and D determine F also. Okay, so this is basically the closure of functional dependency. Now, if you observe clearly, so basically this function dependency is a subset of closure of F. Okay. Any question, any doubt here?
So what this closure means here? Are we supposed to write all these relations, Armstrong axioms related relations?
Related relation? No, you have to check whether from this functional dependency you can derive more functional dependencies or not. So basically, you have to take the closure of functional dependency.
Okay,
So
all possible set of
all
all
possible.
possible
Yeah.
set of all possible dependencies.
Set of all possible dependencies.
Okay.
Yeah.
Okay, got it.
So this will be helpful while dealing with lossless decomposition. Okay.
Why are we further decomposing determining EF as determining E and determining F?
Okay, say suppose during decomposition theorem, okay, we'll discuss one example here. Okay, say suppose I have to calculate the closure of. Okay, so D determine E. I have to make one example. Okay, so let us take here what did D determine C also. Okay, now here D is determining C also. Now this D is determining C and E also. By using this union, we can say that D determine CE. Now, if we take directly the decomposed theorem, we can say that the closure of a D is CE directly. Okay. Now this may not be a correct example for this, but we will require to decompose this thing if we want to perform some this Armstrong axiom between these two functional dependencies. Okay.
Decomposition means breaking the right hand side, right? So you're telling about that. I mean, what are you meaning by decomposition?
Yeah, that's what he meant. Separating into D to EF, he's separating into D to E and D to F, right? That's what he meant.
Yeah.
Yeah. So see, if you can do it in mind, then it is okay. Otherwise, it means the same thing. There is no technical difference between that. But one problem that you will face in further while you learn, there is a process where you actually minimize the functional dependency set. That is, F is a functional dependency set given to you, right? Now, F plus, which we also call as F closure, is that set of functional dependency which we can create using F. All the functional dependency that can be created using F by applying the Armstrong rules is F closure, which will have all the dependencies possible. Now, another further concept that you will learn is minimizing the set of functional dependency so that it still holds all the means you can derive all the functional dependency from that set. That is, the F closure remains set, but F is the minimum set of functional dependency. With only considering those minimum set of functional dependency, you can still arrive at the same F closure, right? So this, while deriving this minimum set of functional dependency, there will be a particular step where you have to eliminate some attribute. So in that step, this decomposition would be required, and that is compulsory. Here it is optional. Here you can do it in mind also if you want, but in that step, yeah.
Even otherwise, if you have a transitivity, say D to EF, and then you have another E to G, but just simply by looking at D to EF, you may not be able to, imagine that there is something called D to G in there, right? So if you decompose, it becomes clear. See, when there are just 4 or 5, as Bhaskar said, there are just 4 or 5, you can do it as a mental calculation. But there may be really big tables. There are about 20, 30 dependencies. And it's good to decompose it so that, even if you want to write an algorithm or write a program to compute the functional dependencies, then if you separate it into 2, it will be much easier. A simple example is what I just said. You have some D from E to F and you have from E to G. So unless you decompose the D to A and D to F, might be slightly difficult to see that there will be a functional dependency, which is D to G, which can be arrived from using these functional dependencies.
Yeah. So F is a subset of F plus. In this case, there's for the in F there is D determining EF. So from F plus, if I am making F again, then there will be an intermediate step to calculate D to E, and D to F means D to EF.
Yeah, you can have just union, right? If you have F plus, the way it is given now, you can have the union rule and you can simply go back to the D to EF dependency in F.
Correct. Oh, thank you.
Okay, mainly see that's ma'am, as ma'am rightly pointed out, it becomes very complex, very difficult when you actually see means the undecomposed functional dependency. Okay, but one thing that you here still, if you want, you can do, but in one step that is compulsory is removing the extraneous attribute. In that step, it is compulsory to decompose the right hand side. Otherwise, you will not be able to actually do it in many problems. Okay, because there we will learn about that in maybe in the practice session. That yeah, ma'am will only teach that canonical cover. So there you will see that this thing is happening. Okay.
Okay.
Yeah, as Dhanya ma'am has given example that we determine G. Okay.
So
So
tutorial is there, I think. Ma'am, the tutorial is there, no?
Tutorial is there.
canonical cover,
Yeah, I am yet to add it to the portal. I will add it today. We've got it on YouTube. I'll add it to the portal today. I'll inform the team and I'll add it today.
Okay.
Sir, can you explain actually the meaning of the F plus and what's use of that?
Plus. So basically, we have to find all the possible combination of functional dependencies. As ma'am said that if we want to determine D, determines E, if this condition holds true or not, but just looking at D determine EF and E determine E, you cannot tell. Okay, so for that you need to decompose this. That is D determine E and D determine F. Now from here you can say that by using this transitivity rule, D determines G. Okay. Okay. Sorry, here G.
Yeah, G.
Yeah. So if we we'll discuss few examples on lossy joint decomposition where many functional dependencies are there. But if we want to find out any closure of particular attribute, we need to decompose this, or we need to do Indian of this. Okay. Okay. Any more question here on this topic?
Yeah, one question is there, sir. In the decomposition, it's written if alpha tends to beta and gamma. So we can say that alpha and beta and gamma, it's the set or set of attributes. Anything.
Set or set of attributes. Yeah. Alpha or beta can be an individual attribute also or set of attributes also. Yeah.
Yeah. So what happens if alpha tends to beta gamma, then alpha to beta and alpha to gamma beta decompose? And what happens if there is a relation between beta and gamma too?
There is a relation between beta and gamma too.
Yeah. If there is also
what is the problem in that? I mean, if there is a relation between beta and gamma, that would still hold.
So there will be any other table we need to make, ma'am, or simply I will only two decomposition is enough?
Okay, so that depends on how beta and gamma are related, right? So beta could be, beta may functionally determine gamma zeta or something, or it could be simply beta determines gamma. In that case, one of these can be removed, right? So it depends on what kind of functional dependency actually holds between beta and gamma.
In that case, if suppose beta holds gamma.
Beta determines gamma, is it?
Yes, in that case.
Okay, and then?
And whatever the rest is there already there. I'm just adding one more.
Yeah, see if so. Okay, let me just ask you. In that case, alpha determines beta, beta determines gamma, and then we already have alpha determines gamma, right? By transitivity also that holds. The three relations hold now.
Yes, yes.
What you're saying is, what if beta determines gamma, right?
Beta, yes, means there is any relation between beta and gamma too.
Yeah, so that's what I'm saying. So if there is a relation between beta and gamma, then that is very specific to what is that relation. There could be more attributes involved on the left hand side. There could be more attributes on the right hand side. It could depend on how it is. But if you say it is like simply beta determines gamma, then already we are saying alpha determines beta. That is the premise of the union, the first statement, right? If alpha determines beta is true is what we are saying. Now you are saying that there is another one which says beta determines gamma. Then clearly alpha determines beta also holds because of the transitivity rule, right? Transitivity rule, right?
Okay.
Yes.
But one thing here, ma'am,
Yeah.
suppose if beta, by mistake, I told that beta determined the gamma. Through transitive rule, we can verify that alpha tends to beta and beta tends to gamma. So alpha tends to gamma itself.
Okay.
In that.
Sorry, it's a question you're asking. What is it?
Yes, I'm telling that by mistake I told that beta determined gamma.
Okay.
And already in the question is given that alpha determined beta and alpha determined gamma.
Okay.
So here transitive rule is verified.
No. We are not saying beta determines gamma here at all. This is some assumption additional assumption that you have given now. In this union statement that we have given, the only premise that we are assuming is that alpha determines beta holds and alpha determines gamma holds. The relation between beta and gamma is something that you defined just now, right?
Yes. So the question is there in the question number decomposition, alpha determines beta and alpha determines gamma. We can't say, can we say that beta determines gamma?
No. We cannot say anything about beta and gamma.
Okay. So it is certainly possible alpha can determine beta and it will be the individual case.
If alpha determines beta, gamma is right, then alpha determines beta and alpha determines gamma is true. See, just simply imagine a table in which you have say a primary key. Okay, just simple example. This, please don't exactly translate to the functional dependency. Okay, just think that there is a primary key. Okay, which is say primary key, the employee number or the student roll number or something. Okay, the student roll number is determining the student name, suppose. And the student roll number is also determining the student's age or something. Okay, got it, no? So in that case, the student roll number determines the name and the age. That is all what we are saying by the union rule.
Okay.
It determines that combination of attributes. That's all what we are saying.
Okay, only that much simply.
Yeah, it's if you take an example of a primary key, it will be like you can see it very clearly. But please don't misunderstand that alpha is always a primary key or anything. I'm just giving an example so that you're able to relate, you're able to understand what this union and decomposition actually means.
Okay. That's, I think once example we will come to, then it will become more clear.
Yeah, okay.
Yeah, okay.
See, if you work out all the problems in the activity question, the practice assignment, everything, no, I think you will get a good hold on this. You can also work out the examples which are there in the textbooks. The familiarity is what makes it easy for you. The more practice you get, the immediately you see something, it will immediately occur to you, okay, I can try all these combinations. I mean, a lot of things, with practice, it becomes a habit, right? That way, if you work out a lot of problems, it will become much easier. The first time you see it becomes a little difficult. The second time it gets easier. The third time it becomes much easier. Okay.
The one thing I wanted to tell about the week 5, ma'am, that this entire week, that all of this is the theory. So we need some tutorial on the example to understand. And I want to, it is good to, if you give the overall view of the motto of the week 5, because entire week 5 video is talking on this idea. And after 3-4 lecture, everything got mixed up. So I want to know the overall idea.
Okay, I get your point. Yeah, I mean, we understand that this is a slightly difficult topic. That is totally understandable. We in fact have 2 tutorials. I'll upload it today. In spite of watching that, if you still have an issue, please let us know. We'll try to have more tutorials. Okay.
Okay.
We can do some problem solving tutorials and all that. We can record and we can release it. I mean, if you are more specific about what are the exact topics which you're finding difficult, we can record something more specifically on that. The two tutorials that we have today, I'll release it today itself. We should have done it yesterday or something, but I kind of got a delay. So I'll release it today itself. And after watching that, if you still have an issue, we'll upload more. Okay.
Okay, sure.
Okay. Shiv Kumar here. Beta determines gamma depend on data set. Okay, it may hold true or it may not hold true. Okay, so it depends on the data which is given in the table. Okay, so you need to try more questions on that. You can practice it. Okay, so with okay. So now in the discourse, yesterday I have seen 2-3 people posted one question that how to find the candidate key. Okay, so I have taken few examples. This is this activity question only. So
Yes,
first,
sir.
yes.
Yeah, sorry for interrupting. So one question on discourse regarding, since we are on the F closure thing, the closure set of functional dependency, I would like to just mention one question on discourse that was there, that what do we mean by soundness and completeness of functional dependency set in the slide? So where professor is teaching,
Okay.
so in that one of the slide he mentioned that while we compute the closure, it is actually sound and complete. So what do we mean by the term sound and complete? So I would just like to mention that. So when you find the closure, that means you are finding it from the given functional dependency set, right? So when you are actually finding the closure for that, it will be sound. That means it will not generate any dependency which is out of the main origin functional dependency set that has been given, because you are only using that to compute the closure. You are not incorporating any other functional dependency which is from outside. Only you are applying the Armstrong axiom, and then you are actually deriving the F closure. So it will, whatever functional dependency, extra dependency that we get in F closure, that is actually derived from the original set given to you, and that's why it is sound. That is, it will follow the rules accordingly. And complete means it will have all the functional dependency. I think that is the definition of F closure, that it will have all possible functional dependency. Okay. Yeah, so I just wanted to mention that. Okay, you can continue, sir.
Okay, thank you, Bhaskar.
Yeah.
Now, first, basically, what is the candidate key here? So basically, candidate key are the attributes or a set of attributes from which we can determine all the attributes in a relation R. Okay. Now here we have a relation R having A, B, C, G, H, R, and having this functional dependency set. Now we have to find out how many candidate keys are there in this relation. So, okay. So basically, what you have to do, you have to take the closure of individual attribute and see whether it's determining all the attributes or not. Okay. So suppose if we take the closure of A, that is A plus. So from A, okay, can we determine? Yeah, from A we can determine B here. So that is B. Okay. Now if you take the closure of AB, further we cannot determine whether we can whether this relation will have all the attributes or not, because there is no functional dependency on B here. Okay, so this closure of A plus is AB only. Now, so this is not a candidate key. Now let us check for B plus. Now from B we cannot determine anything because there is no functional dependency from B tends to anything. Okay, right? Similarly for C, G, for G plus, if you see G determines CH, so G determines CH. Okay. Now further we cannot determine anything here. So this is also not a candidate key. Now we have to check for H plus. Now H plus cannot determine anything. No. Now I no, right? So basically, individual are not a candidate key here. So individual attributes are not a candidate key here. Okay, so then you need to take a combination of AB, BC, CG, or AC. Okay, so different combination you need to try. But the one main trick is that here you need to consider the right side of a functional dependency set. Okay, so attribute which is not present on the right side of a functional dependency set, that set we have to take. Okay, say here that is B, C is there, H is there, and G are. So B is there, C is there, G is there, H is there, and I is there. Okay, so A is not there. So A must be a part of candidate key here, because simply A plus is giving us AB. So A is not a candidate key. Now let us try the combination of different things like A, B. Now if you take AB, we cannot determine anything because AB is not a candidate key here. Now let us take AC. From AC, can you say anything? No. Let us take AB here. Okay, wait. Yeah, sorry. From AC, if you take a closure of AC, it is AC. Now here, A determines B. So from that, we can say ABC. Now from this BC, we can say GI. From BC, we can say GI. That is A, B, C, G, I. So basically what I am doing, I am calculating the closure of this thing. Okay. So So the closure of AC is ABC. The closure of ABC is ABCGI. Now from G, I can say CH. So A, B, C is already here. So A, B, C, G, H, I. Okay. So I get a relation here. So I can determine all the attributes of a relation R from this particular set of attributes, that is AC. So AC is the candidate key here.
So can you explain how you got the last one, ABCGHI?
Okay. Now let us take the closure of this. Okay. Now A, B, C, G, I. Okay. Now if you see the functional dependency of G, G determines CH. So I can say that A, B, C, G, because C is already here. So I write CG here. From G we can determine CH. It means CH is there. Okay. And I is from this. Got it?
Yes, sir.
So
okay,
how
say
did we take AC in the first step?
Sorry?
How did we take AC in the first step?
AC in the first step. Okay. So first we have to find out those attributes that are not present on the right side of a functional dependency. So in this case, A is there. Okay. Now if we take the closure of A, can we determine all the attributes? No. Then we have to take all the possible combination of A, that is AB, AC, AG, AH, and AI. Now I have taken A. Now I have taken AB here. So we cannot determine all the attributes from AB. Now I have taken AC here. Okay. From AC we can determine all the attributes of relation R. So AC is the candidate key here. Now I have to check for further combination, that is AG also. Now similarly, here you can say A determine B. So if I take the closure of AG, so A determine B. So that is B here. Now GB. From G I can determine CH. So A, B. From G I can determine CH. G, C, H. Now here B and C is there, right? Now from this functional dependency, I can determine GI. So that is A, B, G, C, I, H. Okay, so it is equal to relation R. So I am getting all the attributes of relation R from this set of attributes. That is AG is also a candidate key here. Okay. Now let us take, yes.
Sir, while finding these closures, we are not writing here arrows. You are writing it without arrow. Is it okay to write?
No, it is not okay. For explanation purpose, I am writing this. Okay.
Okay. Yeah.
Basically, it is derived from.
So it should be written for A plus. It should be written as A arrow B.
It should be written
A arrow B, na? For A plus, very first one that is written on that.
Yeah. So it is derived from A arrow B, right?
Okay. Because in videos it's with arrows and here it is without arrows.
No. For this explanation purpose, I am writing this down.
So similarly, this A, B, G, C, H, say A arrow B, arrow G, arrow C,
arrow B, and here I have this is determined from G arrow C H, and here from we can say that from BC I have determined GI. Okay.
Okay, sir.
Yeah.
So
now, yes. Just go ahead.
Line you've written A, B, G, C, I, H. So you've written G after B and I after C.
No, that is not necessary. You can write it as A, B, C, G, H, I, or anything. Basically, we are finding the attribute set only here.
This is a set. Okay. So this is basically a simply set.
A, comma, B, comma, C, comma, G, comma, H, comma, I.
Yeah, Piyush sir, you can put the curly braces on as an example on one of them and just tell them. So these are basically a set and nothing else. Each step you have to mention that which functional dependency you are using. If you are writing in a subjective examination, so that whenever you proceed to a next step by applying one of the functional dependency, you just mention in bracket as Piyush sir has mentioned at each step that in the next step I am using this functional dependency to add another new attribute in the set that I have achieved till now, and accordingly I will proceed till I get exhausted of all functional dependency that I can apply to increase the set of attributes. Okay, so the closure set of any closure set is basically a set. That's why we call closure set. So you can write in any order, that doesn't matter.
Yeah. In subject exam, you have to write, say, let us take a closure of AG plus, and by using A determine B, and we are getting A, B, and G. Now in the next step, you can write by using this functional dependency, that is G determine H, we are getting A, B, C, H, and G. Okay. So this is a basic way of writing, because from this function dependency we are deriving this all the set of attributes. Okay. Now here AC and AG are the candidate key. Now let us check for other combinations also, that is AH and AI. Now from A, okay, so from A we can so basically if we take a closure of AH, so you have to consider AH here. Okay. Now from A determine B, so I can write A, B, H. Now is there any other function dependency holds true here? No. So this is not a candidate key. So AH is not a candidate key here. Similarly, AI, that is AI, from A determine B, I can write A, B, I. If you take the closure of ABI, can we determine further? No. So this is also not a candidate key. So we have two candidate key here, that is AC and AG. So answer is 2. Okay. And one more important point is that the attribute which belongs to the candidate key is known as prime attribute. Okay. That is prime attribute. So attribute which belongs to the candidate key. So here A, C, and G. So these three are the prime attributes and other are non-prime attributes. Okay. Any question here?
Now in this example, you only check combinations with A. Like you don't have to do it the other way, like B to A or CH to G.
No. See, initially we have to calculate the closure of all the individual attributes, right? We cannot determine anything from that. But the basic trick is we have to take those attributes which is not present on the right side of the functional dependency. So here it is A. So A must be a part of candidate key. Now if you take, say, okay, say here it is AC is a candidate key. Now if you take any combination of attribute with AC, say ACB or ACG, then it will obviously determine all the attributes. But these are the super key, not the candidate key, right? It is a super key, not a candidate key, right?
So we can't do like from G, like we're taking ACG, but that would be super.
From G, sorry, I didn't get you.
Like we started taking combinations like AC, AG, AH. We didn't do G, A or G, B or anything like that. We only started from A.
When we start from A, because A is not there in the functional dependency, that's why we start from A. Okay, we'll discuss with one more example here.
In the previous example, I mean,
okay,
in the functional dependency set, the attribute which is not on the right hand side, we start from there, correct?
Okay.
So
yeah, right.
is that a rule or just by so many observations?
No, it's a trick we have observed. There's no observation. There is no specific rule for that.
I asked because suppose there would have been a dependency in which all the attributes would have been there. So can we? Is it safe to assume that one of them will definitely be a trivial?
Yeah, no. That is not safe to assume. So see, basically, what I think the doubt that's why it is not getting cleared. So at first, tell me what is the condition? What is the property of a candidate key in terms of closure set? If you all have watched the lecture,
K determines R, and there is no subset of K which can determine R.
There is no subset of
K determines R, and there is no subset of A which can determine R. Not that. What I am telling about is, so basically, when you are finding the closure set of a candidate key, it should have all the attributes. So is it correct? You all have learnt about that, right? So you are finding the closure set of a candidate key. So suppose in this example, AG is a candidate key. So when you find the closure set of AG, that is AG plus, the rule is you should get all the attributes in the closure set. If you get that, then you can safely say that AG is a candidate key. Whatever, yeah, so it is a key, not candidate key, it's a key that you can say. Now it should be minimal, and then you can say candidate key. So the process of observing the right hand side, that is a trick. It's not anything a rule or something like that. It's a trick, because if you want to have all the attributes in the closure set, and on the right hand side of any functional dependency one attribute is not there, then how can you get it in the closure set? Just think about it. You are deriving the closure set by simply using the given functional dependency. You are applying the functional dependency in each step and adding one attribute to the closure set that you have achieved till now. And at one point you will get exhausted of all the dependencies and you will say, so this is the final closure set with respect to that attribute which I got, right?
And that final closure set will not have all the attributes of relation R.
If it does not have all the attribute, then that attribute of whose closure set you are calculating, that is not a key for sure. If it is a key, it should determine all the attributes. That is the rule. So please, yeah, so this is the most important thing. I think this point was missing, and that's why you all have not seen that part of the video, I hope, I think. Anyways, so the rule is, whenever you are finding the closure set of with respect to one attribute, two attribute, or a set of attribute, whatever, if you find all the attributes at the end in that closure set, then you can safely say that the attribute of whose closure set you are calculating, that attribute is a key. Now it can be a super key, it can be anything, right? So this is the first property that you have to understand, so that it is a key. Now coming to candidate key is, as you have mentioned, as Mr. Bimlesh has correctly mentioned, that you cannot have it is a minimal thing, right? You cannot have a smaller version of it which can determine all the attribute. So that's why the process to do that is, we will just take one attribute and add one attribute and check whether it guarantees that it will have all the attributes set in the closure, right? So how can we do that? That's where this observation comes, that we will start from one of the attribute which will not be there in any of the functional dependencies right hand side. Now why it is so? It is so because you are using the functional dependencies to form the closure set, correct? But if any attribute is there which is not there in right hand side of any of the functional dependency, can you get that in the closure set? You cannot
Not
get
possible.
that. You cannot get that. With whatever combination of functional dependency you try, you will not get that. So that's why the trick is, you have to consider that attribute if you are trying to find the key. So you must have all attribute, right? So you have to consider that attribute in the key itself, because then it becomes trivial. Because you take it in the left hand side, then it will obviously determine itself. That's why it comes on the right hand side also. So whenever you see that one attribute which is not there in any of the functional dependencies right hand side, then you can be sure that it is in all the possible candidate keys. Got it?
Yeah, thank you.
Yeah, okay.
Okay.
Yeah, you
So,
can continue.
yeah, say suppose instead of finding how many candidate key, we have to check whether AGI is candidate key or not. So in that case, what we will do, we'll take the closure of AGI. Okay. So now from A determine B, I can say that AB, G, I. Okay. Now similarly from G determine CH, I can say that AB, G, CH, I. Okay. Now this is equals to relation R. So yes, AGI is a key, but whether it is a candidate key or not, for that we need to check the subset of this attribute, whether it is a minimal key or not. So say suppose A plus is not a candidate key. Now let us take closure of AG. So AG is the candidate key here. Okay. So AG is the candidate key here, and AGI is a super key here. I think there is one slide in the lecture where Saras mentioned the same thing. First, Saras check AG is a super key. Then they have done whether it A or G determines R or not. Okay.
If left to be done manually, it's very time-consuming process.
Yeah, basically, I want to explain those things as a procedure. That's what I have done. So best trick is to find out the attribute which is not present on the right side of a functional dependency. That's it. Okay.
Piyush, I'll just add one point. I'm not sure how many of you actually noticed it, but see if you what exactly do you mean by a candidate key? A candidate key is something that can uniquely determine a tuple in a relation, right? It identifies the combination of all the attributes in a tuple. The candidate key or the primary key is a unique identifier for a tuple. And that's what we are precisely meaning by saying that the closure results in all sets of attributes. That is, this candidate key is capable of determining a combination of all the attributes. That is how it translates to the functional dependency in finding the functional dependencies. I'm not sure whether you have already related that, but that's what it means eventually. You probably know already, right? That a candidate key is something that uniquely determines or uniquely identifies every tuple in a relation. So here also, that's exactly what it is doing. Every attribute, the whole attribute contributes a relation, and every tuple is actually determined or uniquely decided, or it kind of identifies that particular all combinations of attributes. Okay, Piyush, carry on.
Okay. Now next example, same example is there. Just we have to select the correct option. Whether AG is a candidate key or not. So it is not a candidate key. AG is a super key. Yes, it is candidate key and super key also. AG is the primary key. If it is a key, it is a primary key. Yes, this is also correct. Now closure of A plus. Now from A we can determine BC, and from B we can determine I. So A, B, C, I is a closure of A. So these three options are correct. Okay. Now next activity question here. Now see here, we have to find out which of the following are the prime attribute. So same procedure is there. First, we have to find out all the possible candidate key here. Okay. Now we have to, if we follow the same procedure, if we take the closure of individual attribute, we cannot determine all the attributes, right? Now, what I have said that we have to take those attributes that are not on the right side of a functional dependency. Now here, C is there, B is there, and E is there. So C, B, and E. Right? So A and D is not there. So we have to take A and D. Okay. Now we have to take the closure of AD. Okay. Now from this functional dependency set, can we determine R here? Okay. So I have A and D. Okay. If we take the closure of AD, can we determine any further? No. So now let us try the combination of AD. Now let us start with AD and B. Now let us take the closure of ADB. That is A, D, B. Okay. Now from this function dependency, that is A, B determines C, we can say that A, D, B, C. Okay. So basically it is from A, B determines C. Now by using other function dependency, that is C, D determines E. So that is A, D, B, C, E. By using C, D determine E. So I am getting here R, that is A, B, C, D, and E. Okay. So ADB is a candidate key here. So ADB is candidate key here. Now let us try for other combination, that is A, D, and C. Okay. Now say A, D, C. Similarly, here from CD I can find E. So that is A, D, C, D. Now from DE I can determine B. So A, D, C, E, B, and from AB I can determine C. Okay, so already is here. Okay, so it is also equals to R. So our ADC is also a candidate key. So ADC is also a candidate key. Now let us take another combination. That is last one. That is A, D, and E. Okay. Now if we take the closure of ADE, so from DE I can determine B. So A, B, E, B. From AB I can determine C. That is A, D, E, B, C. This is equals to R. So ADE is also a candidate key here. Okay. So there are three candidate keys, that is ADB, ADC, and ADE. Now the prime attributes are those attributes which are there in the candidate key. So A is there, okay, B is also there, C is also there, D is there, and E is there. So all the options are correct. So all the attributes are prime attribute here. Any doubt in this? Okay. No question. Shall I move on to the next topic? Okay. So now we'll discuss about lossless and lossy joint decomposition. Okay. So I have recorded one tutorial on this. Please go and watch those tutorial. I will quickly go through it first now. Okay. So this is the same example I have taken from the slide only. So suppose there is a supplier part relation having attribute supplier ID, SN, city, part ID, and quantity. Okay, now having functional dependencies like this. Now, if we decompose this table into supplier and part having this attribute, we have to find out whether our this decomposition is lossy or lossless decomposition. Okay. So now first we need to understand what is lossless and what is lossy decomposition. It's lossless and lossy decomposition. Okay. So suppose I'm determining one big table. I'm decomposing one big table into two or more small different tables. So if I join those tables, I should get the same table, right? So basically, what I am saying is, suppose this is relation R, this is R1 and R2. Okay. Now I decompose this relation R into R1 and R2. Now when I perform the natural join between R1 and R2, I should get the same relation R. Okay, so then I can say that our this decomposition, that is R1 and R2, is lossless decomposition. If it is not equal to R, if we are getting some extra tuple or less tuple, then we can say that our decomposition is lossy decomposition. Okay, now in this case, if you perform the natural join operation between R1 and R2, you will get two more extra tuple. Okay, yeah, you can see here I am getting this two new tuple here, which is not there in the original table. So this decomposition is lossy decomposition. Okay. Now, if I decompose the same relation into this, like I suppose it's R1 and R2. So initially, what we have done is R1 SID, SN, CT, and quantity. And here, what I have done SID, SN, CT in relation R1 and SID, part ID, and quantity in relation R2. Now, if you perform the natural join operation between R1 and R2, I am getting the same table here, that is original table. Okay, here you can see I am getting the same table. So this decomposition is lossless decomposition. Okay, so there are specific conditions from which you can directly determine whether our decomposition is lossy or lossless. Okay, any question, any doubt in this?
Order doesn't matter, like of tuples in our relation when we get it as the output.
Sorry.
So when we do natural join, if we don't get the same order, then also it is lossless, right?
If we get the same original table, then it is lossy.
Order should be same of all the tuples.
No, not order. If we are getting extra tuple or less tuple, then it is lossy decomposition.
So order doesn't
Order
matter.
can be anything. Yeah, order doesn't matter. Okay, so now there are some specific conditions from which we can determine whether our decomposition is lossy or lossless decomposition. Okay, so first condition is R1 union R2 must be equals to R. Second one is R1 intersection R2 should not be equal to empty set. And third condition is R1 intersection R2 to determine R1. It may be R1 or it may be a key from which we can determine R1. Similarly, or R2 here. Okay. So if you see the previous example here, if you perform R1 union R2, I am getting SID, SN, CT, SID, it is part of PID and quantity. So I am getting equals to R. So I am getting all the attributes which is there in the original relation R. Now our first condition is satisfied here. Now let us go for second condition, that is R1 intersection R2. Now the common attribute between the supplier and the part is SID. Okay. So it is not equals to empty set. So our second condition is also satisfied. Now we have to see whether we can determine R1 or R2 from this SID. Okay. Now by using this functional dependency, we can say that SID determining S name. So if you take the closure of S slash, we can say that S slash comma S name, right? And from S slash we can determine city also. It is S slash S name and city. Here I am getting relation R1, that is S/S city. So all the three conditions are satisfied. Now this decomposition is lossless decomposition. Okay. Any question? There are few examples given in the slide. You can try it out. Okay. So I will discuss few examples here. Rest you can try. Okay. Let us check for first example here. So consider this relation R having A, B, C and having functional dependency A determine B, A determine C. Okay. Now let us check for first condition. That is R1 union R2. Okay. So R1 union R2, we are getting A, B, C, which is equals to R. So our first condition is satisfied. Now second condition is R1 intersection R2. So R1 intersection R2 equals to B. Now it is not equal to empty set, so this condition is also satisfied. Now let us check for third condition, whether B is determining R1 or R2. Okay, now if we take the closure of B, can we determine R1 or R2 from here? No, because there is no functional dependency which can be derived from B here, right? So in that case, our third condition is not satisfied. So this decomposition is lossy decomposition. Okay. Any question, any doubt? You can try different examples. Okay, I guess no. So let us go for second example. Okay, now here I have decomposed this relation R into R1, R2, and R3. Now in that case, what I have to do, I have to check for first condition, that is R1 union R2 union R3. So it must be equal to the relation R, that is A, B, from here CD, and from R3, that is EF. So which is equals to R. So our first condition is satisfied. Now what is our second condition? That is R1 intersection R2, right? Whether you can take this combination of these two or any two. Okay. Now I will take R1 and R2 only. Now the R1 intersection R2, what is that common attribute between R1 and R2? It is B here. Okay. So now if we take the closure of B plus here, can we determine R1 or R2? Let us see. So okay, from B determine C, I can say BC. Okay, and from C determine D, I can say CD. So B, C, D, which is equals to R2. Right? So our third condition, that is R1 intersection R2 is determining R2. So this condition is satisfied. Now we have to check for this R3 also. So we already taken the combination of R1 and R2. So let us give a name, say R12, which is equals to R1 union R2. So which is equals to A, B, C, D. So A, B, C, D is a new relation, that is R12. Now we have to check this condition with R12 and R3. Okay. Now R12 intersection R3. Now what is the common attribute between R12 and R3? That is D here, right? So D. Now if we take the closure of D, can we determine R3 or R12? No. Okay, so we cannot determine R3 or R12 from this. Okay, so our third condition is not satisfying here. So this decomposition is also a lossy decomposition. Any question, any doubt?
So what do you mean by R12?
R12, basically it is a union of R1 and R2. Okay, so we already checked for R1 union, R1 intersection R2. You can take any combination. You can take R2 and R3 also. Okay, so let us take R2, R3. So R2 intersection R3. Okay, so the common attribute is D here. From D, can we determine any R2 or R3? No. So we can directly say that this is a lossy decomposition. So basically, you have to take any two combination of the decomposition, R1 and R2, or R1, R3, or R2, R3. Then you have to rename it as R12, which is equals to R1 union R2. Then you have to check this condition with R12 and remaining decomposition, that is R3 here. Okay. Yeah. Similar examples are there. So, okay, I think I have explained this part in our tutorial. It's last question. So here you have to do, you have to see whether the combination of R1, R2 or R2, R3 or R1, R4, any combination is working or not. So let us take R1 and R2 here. Okay, so I already explained with the help in the tutorial R1, R2. So I will take R1, R3 here. Okay, so R1 intersection R3. But before you have to check R1 union R2 union R3 union R4. It must be equals to relation R. If this is not true, then your decomposition is directly lossy decomposition. So here A, B, B, C, A, B, C, D, E, G. Okay. So I'm getting all the attribute here. A, B, C, D, E, G. So our first condition is satisfied. Now let us, I take R1 and R3. Any common attribute is there? AB, yes, AB. Now if I take the closure of AB, can I determine R1 or R3? AB, this is AB itself. So relation R1 is AB only. Yes, I can determine R1 from that. So first condition is satisfied. Now this combination is satisfied. Now you have to check for this remaining combination, that is R2 and R4. Okay. Now R2 intersection R4. Is there any common attribute between them? No. So our second condition is not satisfied. So basically it is an empty set, right? So this decomposition is lossy decomposition. You can take R1 or R2, R1, R3, R1, R4, any combination you can try. Okay. Now if you see the second part, if you decompose into R1, R2, and R3, here let us check. Okay, R1 union R2 union R3 equals to A, B, C, D, E, G. Okay, so it is equals to R. So first condition is satisfied. Now let us try for R1 and R2. Okay, so R1 intersection R2. So the common attribute between R1 and R2 is AC. Okay, so AC. For AC, can I determine R1 or R2? Let us see. Let us take the closure of AC. That is AC plus. Now from AC, I can determine B here, right? So that is A, C, B, which is our R1. So this condition is satisfied. Now say let R12 equals to R1 union R2, which is equals to A, B, C, D, and E also. Now I have to check whether R12 intersection R3 satisfied or not. So R12 intersection R3. The common attribute between R1 and R3 is A, D, and AD. Okay. Now we have to check from AD we can determine R12 or R3. Now let us take a closure of AD here. Okay. Now from AD we can determine E. Okay. So that is A, D, E. Now yeah, here you can from E to D we can determine G. That is A, D, E, G. So A, D, E, G. Yeah. Okay, from this we can get R3, that is A, D, G. So all the conditions are satisfied. Now this decomposition is lossless decomposition. Any question? Any doubt? We have recorded one tutorial also. You can watch that tutorial. Yes, anyone? That's it. Okay. Okay, so if no one has any doubts, so we can go for activity questions. Am I audible or not?
Yes, sir, you are.
Yeah.
Okay, okay. Okay, so what you have to do? You have to go to menti.com and use this code. Okay. So here you will get time for each question. Okay, if you answer within a time limit or less time, you will get more points here. Okay. So we will try different things today.
Yeah. So I think Arup sir also suggested to solve 2 questions. I think I will just solve that and then we can move to menu.
Oh yeah. Okay, sure.
Yeah.
Okay. I will stop sharing.
Yeah. So these questions are basically from the activity question only. So yeah, I would just like to mention that it's similar on the similar lines only, same questions like the ones that you sirs just taught all of you. Okay, just a second. Yeah. So this is basically the activity question number. Okay, I'm just writing it. Hello, am I audible?
Yes,
Yes,
Bhaskar.
Bhaskar.
Yes, very
Yeah.
much.
Yeah. Okay. So basically the question states a relation is given to you R and it is A, B, C, G, H, I. Okay, and the functional dependency set corresponding to it is given, right? Okay. Okay, so first of all, I want to just say, please honestly reply who all have doubts in the candidate key definition with respect to closure set, because it is a little bit not complex, but yeah, in the first view it is a little bit difficult to understand. So I would just like to see if anyone has doubt in that. Yeah, you can raise your hands now. Okay, so anyway, I will mention it shortly. Okay, with 2-3 participants we have. See, so as ma'am rightly pointed out, first any one of you please unmute yourself and tell me what is a candidate key.
Which can decide tuple uniquely.
Which can decide all the tuples in the table uniquely,
Yes,
right?
sir.
Now, the functional dependency definition is clear for all of you, right? That we can have if two tuples are there, if T1 is a tuple and T2 is a tuple, two tuples are there and two attributes are there, A and B, suppose two attributes are there in the table, and we
Yes.
will say A goes to B is a valid functional dependency only when this will happen, that whenever A is repeating, that is A1 is there, A1 is there, then B must also repeat. Whatever B is over here, suppose B1 is over here. So if A1 repeats at any stage, maybe this tuple is after over here. Okay, A1 is here, and here we have maybe have A2, A3, etc. or something like that. Okay, so whenever A1 we find again, it should only be associated with B1. Okay, and another doubt that some of you are giving, I think Kumar was asking, then these are identical. These may not be identical because there can be some other attributes also in the table which may have different value. Suppose D1, D2. That is not an issue. We are only considering this part, the functional dependency that has been given regarding A and B. Okay. Okay. So this is the definition of functional dependency, that whenever the left hand side is repeating in the table, the right hand side must compulsorily repeat. If it is something else, it is not the case. But the vice versa is not true. So if you can A2 over here, you can also have B1 over here also. That is fine. Like we can have many to one, that is many to one. A1, A2 both are coming to B1 actually. So this B1 only. That is many to one is possible, but one to many is not allowed. Right? You cannot have A3 B1 and A1 B1. Okay, so this is not sorry, not A3 B1, A3 B1 and A3 B2 suppose. So this is not allowed. So this is the basic definition of functional dependency. If left hand side repeats, right hand side must repeat it. Now I want you to relate both of them. A candidate key is such a key which will have all, which can identify all tuples uniquely. A functional dependency is a valid one when left hand side repeats, right hand side must also repeat. Now can you relate that why it is so that a candidate key must have all the attributes in the closure set? After Piyush sir's explanation of all these, I hope you should be able to relate that. This is so because since a candidate key must have okay, so what is a closure set? I will mention that once again. If I find A plus, so it is A plus is a closure set. Okay, so this is a set which will have attributes over here that can be directly functionally derived from A. So if there is one functional dependency, A goes to BC, like over here, so I can say that A can derive B and C. So therefore I will mention here B and C. Okay. Now, do we can we derive something else from B? Yes, we can derive I from B because B is over here, right? Left hand side B is there. So once we got BC, the next thing that we can do is we can simply derive I from B, and therefore we can write B, then I is added, and then C. Like this we will proceed and we will get the final set, and that would be the closure set. Okay, so like in this example particularly, this is the final set with respect to A plus. Why? Because you have C, but here you need G also, correct? So you cannot derive H unless you get G. You cannot do it with you only using C. You cannot do. So therefore, using C you cannot add any other attribute because no other functional dependency satisfies that. B goes to I is already done, and A goes to B and C is already done. So this is the final set. Therefore, this is the closure set. This is the closure set with respect to A. Closure of A, which we define as A plus. Now I am saying that any key, and specifically candidate key also, it must have all the attributes. What that means is, since these are actually functionally determined by A, that is, once you get the closure set, you can write something like this. So BIC is in the closure set of A, right? So therefore, a direct correspondence to this closure set is A goes to B. You can write directly like this. A goes to I. So I think Bimlesh or Kumar, someone was asking that what is the utility of deriving the closure set. So it is the utility is that you can derive all possible functional dependency which is not directly given to you. So I just derived BIC. I can say A goes to B, A goes to I, A goes to C. So this must hold in the relation. In this relation, these functional dependency must compulsorily hold. Now A goes to B and A goes to C is obviously visible. You can see that. But A goes to I is something which is not directly given. So this is the new functional dependency that you got, which can be derived using these in 1 or 2 steps by using Armstrong's axiom. Okay. So Armstrong's axiom is the one that we used while deriving it. Anyways, so when you now, if this is functional dependency, it means left hand side must, whenever it is same, right hand side will be same, right? So now I hope you can see why candidate key must have all the attributes, because candidate key uniquely identifies all attributes. Uniquely identify means whenever the candidate key remains same, all the attributes must be same, right? Uniquely identify means that, right? So whenever I have candidate key value as C001, then all the attribute values over here, which are over here, that must be same whenever I have C001 again at some point. That is the very idea of candidate key, correct? Now, if that is the case, that is the same thing which is happening in functional dependency. So we can write that the candidate key CK will functionally determine all attributes in the table. So this is the property. Okay. So now when you have to find who is the candidate key in the table, the best way is you find the closure set and see if the closure set has all the possible attributes, then it is a key. And since you are only considering one by one, you are slowly increasing the attribute set. That's why you can say this is a candidate key because it will be minimal. Now I will show with this example that how to do that. Just user already taught all of these, but just a small discussion on this.
Sir, one clarification I need to clear here.
Yeah.
The example you shown that to find, I understood that how to find the closure set. So you started with the A plus.
Yeah.
So what's the purpose? Whatever the
No,
subset.
no. That is not the purpose. I just gave an example of why a candidate key must have all the attributes in it.
Okay. So it is the recursive in the nature. I have to go one by one.
You have to go one by one. You have to go
until
one by
the end of the graph.
Exactly. That's what I showed, right? That you get exhausted of all other functional dependency. You got C, a new attribute, but with C you cannot proceed because it also requires G, and you did not get G anywhere in the set, right?
Okay. So you started, sir, with A plus.
Yeah.
So what will happen? We start with the B plus.
That will be the B plus's closure. You can do that, no issues. Closure of A plus, B plus, C plus, you can find AB plus, all possible combinations closure you can find. But that is not our motive. Our motive is to find the candidate key, and I have not displayed that. I am just coming to that. I just give you an example of what is the closure.
Okay, that's clear, sir. How much you do?
Yeah, okay. You can find B plus closure. What will be the B plus closure? It will be B. With B, you can take I. So I will be there. But with I, can you do anything else in the next step? There is no other functional dependency which has I on the left hand side, using which you can determine a new attribute, right? Therefore, B goes to I, the closure will be only I and B itself, right?
Okay, yes.
B itself will define itself. So that is trivial. Whenever you have a alpha plus, the set will always have alpha. It will have many other thing, or it may not have many other thing, but alpha will always be there. This is the trivial dependency.
Okay.
Yeah. Now I will go to this question and briefly just discuss this. So, okay. Now once you are clear with this candidate key and closure set thing, now how to get the candidate key, how to get started with it, that's where the doubt is coming, and that right hand side should be there or not. So see, there is no hard and fast rule. You have to check the right hand side. In many cases, you will not get in the right hand side some attribute is missing, as Bimlesh was saying. There is no specific way or algorithm to find candidate key like that. You have to check all functional dependency, and you have to find the closure set of all attributes, all possible attributes. You have to find the closure set of attributes considering singly. So A, B, C, ... Then you have to consider A, B, B, C, ... all two combination. Then A, B, C, B, C, A, whatever, all possible three combination. Now this becomes very troublesome, right? Also, so therefore the best way is to proceed incrementally, because if you add one attribute and check whether the closure set incorporates all other attributes or not, you can be sure about one thing, that it is minimal, right? Because you just adding one attribute and checking. So that way you can be sure that this is a candidate key, not a super key, not any other key. It must be a candidate key because I have added one attribute and checked. So that is one point. And the right hand side point is, if you do not have any attribute on the right, if an attribute is not in the right hand side of any functional dependency, can you get that attribute in the closure set while you are calculating? You cannot get that over here, right? Because no one is determining that. The only way to get that in the closure set is to keep it in the left hand side itself, because just we show that in B plus, B will be always be there, right? So that is trivially satisfied. So that's why the trick is that which attribute to start from. That's why we say that always see the right hand side and check which attribute is not. So what will be the candidate key in this relation? Okay, let us check B, C, H and I are there. So B, C, H and I are there. A and G, these two attributes are not on the right hand side. So therefore, in any possible closure set, you will not get A and G if you do not have A and G left on the left hand side itself. Got the point? So therefore, one thing you are sure that in order to get all attribute in the closure set, so that we can call it as a candidate key, we must have AG in the closure set because it's in the relation. It is a part of all attributes. And in order to have that, we must have AG on the left hand side, because no functional dependency is determining AG. So what is the minimal possible combination that I can have using both A and G? It is AG itself, right? Let us check with AG only, can we have all possible attributes or not? So can we have, with A we can get B and C. So simply add B and C. Now I have B, C and A. Let us check in my hand. Consider in my hand I have B, C and A. Now I will see what possible functional dependency I can satisfy using B, C and A on the left hand side. So G, C, I do not have G, although I have C, but I do not have G. So I cannot proceed with this. Yeah, so here B is there. I can take this dependency and I will add I because this determines, right? So BCI is satisfied. Now in my hand I have AG, BC and I. Oh, sorry. One mistake I did. Sorry. So you can also have this because G is implicitly there. I did not observe that. A and G you have in your hand. Therefore, A goes to BC is fine and G goes to C you can also apply. Sorry about that because you already have G in your hand. So therefore, you can have GC goes to H. Got the point? I just missed this G. So G goes to C, GC goes to H you can have. And you can also have B goes to I because you already got V over here. Got the point? So B, C, I, H, A and G. A and G will be trivially there. So I think all the attributes are there. B, C, I, H, A, G. B, C, I, H, A and G. Correct? So the minimal set that I got, which was not on the right hand side, that is AG. And with AG only, I got the whole set, right? Therefore, this is the only candidate key possible. Because if you add any other attribute with it, it will become a super key. It will not be a candidate key anymore. Got the point? So this is how you proceed with candidate key. And the question in activity was that what is the closure set of AC plus? Oh, no, sorry, not AC plus. Oh no, sorry. The question was option 1 was AGI is a candidate key. AGI is candidate key. Option 2 was AG is super key. Super key. Option 3 was AG is primary key. And option 4 was A plus. The closure set of A is A, B, C, I. Now, can you tell which option is correct? I want one of you to unmute yourself and tell me. It can have multiple option correct. Huh? It is a MSQ. This is AGI.
So AG is primary key and super key.
Very good. And A plus. What is A plus? Tell me. This we will do together. What is A plus?
It determines BC.
BC, very good.
And then we can get I from the
Very
functional
good.
BI.
And
A is already there.
Very
so
good.
A, B, C, I, fourth option also.
BC, I and A.
Yes.
So BC, I and A. So this is also correct. Okay. AGI is a candidate key. What would have been the correct option if I say that this is not CK but this super key? Then it would be correct or it would not be?
No, I don't think so because we cannot use
I am saying it is a super key, huh? AG is a candidate key, correct?
Yes.
What is a super key? A super key is any attribute added to the candidate key, or the candidate key itself also is a super key, right? So
Yes.
candidate key plus 0 or more attribute equal to super key. Correct? If it is the case, I can, if AG is candidate key that we got over here, AG is a candidate key, therefore we can say AGI is a super key. So it satisfies. Okay, fine. So this was one question, and I would like to just discuss another question. That is a closure set only. I hope all of you are okay with the closure set, right? Or I will discuss just one example. If you are not, someone of you is not, you can raise your hand. Otherwise, I will skip that and we will go back to you, sir. That's why in this question I described closure set at first, so that it covers. Okay. Okay, thank you. So Piyush sir, you can continue, I think.
Hello. Yeah. Thank you, Bhaskar. So we will take some activity question with the help of Mentimeter. Okay.
Just a second, I'm starting soon.
Hmm.
Yeah.
Is it visible? Yeah, you have to go to menti.com and enter this code. Okay. Okay, so you have to enter your nickname. Okay. So I got 3 entries here. How many people are here? Okay, 1, 2, 3, 4, 5. Okay. Everyone join? Only 4 people join it. Okay. Is anyone yet to join? You can unmute yourself. Or I will start. Okay, 5 people. Okay, I guess I can start now. Now here is the first question. Okay, you have to answer within 2 minutes. Okay. If that image is not visible in menti.com, you can see it here. Okay, no issue. Okay, I got first answer, second. Okay. Fourth, okay. One more remaining. Okay. Oh, as you can see the result there only if your option is correct or not. Okay, I guess everyone got it correct. Now we'll move on to the next question. We'll discuss once we complete all the question. Okay, don't worry. Okay. Okay, one more question. Okay. Once everyone answer this timer will stop automatically. Yeah, everyone has voted. Okay, great. Next question. Okay, great. Next question. Oh, what happened? Just 1 minute. Just 1 minute. Is my screen visible now?
Yeah.
Yeah. You can go to next question now. 5 people join, 1 more remaining. Okay. Okay. So we have 1 minute for this question. Okay, great. Next question. Okay, this easy question. You should be able to solve it in 10 seconds only. Okay. Okay, 1% got it wrong. Okay, no worries. Next question. Okay, you have 2 minutes for this question. Okay, so 2 people got it wrong. No worries. We'll discuss this question.
Yeah. I was just going to say that we should discuss this.
Yeah, okay. Next question. Okay, great. Next question. Okay, great. Okay, so next question, I think the last question is. Someone has answered within 15 seconds. Okay. Don't do cheating, guys. Okay. Within 15 seconds, you are answering this question. After you have solved this question in activity, then it is okay. Okay, great. Bhaskar, we have to discuss this question, I think.
Yeah.
We'll discuss that. Okay, no issue. So now let's see the result.
Result.
Okay, yes. Yes, fasted, Sejal, right?
Yes, sir.
Yeah, very good. Congratulations. Okay,
This is
good
nice.
code, CKG, good, K, Mia. Okay, fine. You should give your real name, yeah. At least we should know who have answered it, who has scored more. Okay, let it be. Okay, so which question we have to discuss? Last one and that trivial function dependency, right? Bhaskar, would you like to take this question?
Yeah, I will take. But the questions, can you show those questions?
Okay. Which one was that? Last one. Okay. It is visible, right?
Yeah, it is visible. For me, it is okay. Others, you can see it, right?
Yes, sir.
How
Yeah,
can I pause
so
this timer? Okay. I will open it in PDF. Just 1 minute. Huh?
yeah, it's okay. That would be fine.
Sorry. Is it visible now?
Yeah, it's okay. Yeah, so acha, so okay, Can you tell me that what was the doubt that you were having on which you answered it wrong? So whoever did that, it's not something, it would be good for us to discuss that, right? Otherwise, I will just go through the whole process.
For me, I mean, I saw that third option, R2 intersection R3 being null set. And that based on that, I chose C.
Yeah, so null set R2 intersection R3, that is null set, that is fine. But while you are actually combining the tables after decomposing, you can do that in any order. Okay, so you can have combinations of R1 with R3, you can have combination of R2 with R1, R2 with R3. You have to check all possible combinations that are there. And in one of the case, you will find, if in any of the case you find that in that particular order, if we combine the tables, then it is not lossless. Then it is lossless. Then we can actually finally have this judgment that the whole decomposition is lossless. So it is not that with respect to each possible combination, there should be an intersection. Okay, so you can join them in any order as long as you get the final table, it is okay. So if you do not have a combination of R2 with R3, or R2 and R3, we do not have any common attribute. That is okay, fine. But let us check with R3 and R1. R3 and R1 we have common as B, correct?
So we can join R1 and R3 and then check for the intersection with R2. Okay.
Exactly. If once we join R1 and R3, we will achieve one extra attribute. What is that attribute?
D.
D. We will get the D attribute because B is common in R1 and R3. AB is in R1, that is fine. So D attribute we will get from R3, and that will combine into a common table. Let us call that R13. Okay, so R13 will be an intermediate table after combining R1 and R3. So that table will have attribute A, B, E, and D. Now, once we have A, B, E, and D, now we will combine R13 with R2. So A, B, E, and D is in R13. R2 has E, so only E is the common attribute. So we need to check whether E goes to C is there in R2 or E goes to A, B, and D in R13. Got my point? In the intermediate table R13, A, B, E, and D were there. So, and in R2 and R13, common is E. Intersection is E. According to the rules of lossless decomposition, you need to have one in any one of the table. The common attribute should functionally define all other attributes. According to that rule, the common attribute between R13 and R2 is E, and therefore E should functionally define either C or all other attributes in R13, which would be A, B, and D. Now E does not define A, B, and D. Is it defining? Somehow B and D it is defining, but okay, so E is actually defining over there. You can do in that way, it is okay. But if you have E goes to C, then it is, you can say that it is actually lossless. Otherwise it is lossy. Got the point? So you can have basically in all possible combination, you can make the call. Not in, it is not that in only one possible way you have to check. Is there any other, another question was there, right? So we can move to that if it is okay.
Yeah, just 1 minute. Which question was that? Based on trivial function dependency, right?
Yeah. Yeah, so trivial dependency, I think it is directly from the definition. So anything which is, if you have an attribute on the left hand side and it is also occurring in the right hand side, then it is a trivial dependency.
So basically trick is, say suppose alpha determines beta. This is a function dependency you have. So, or it make alpha or beta may be a set or single attribute also. Now you have to see whether alpha intersection beta. If there is any common attribute between these two attribute set, then we can say that it is a trivial function dependency. If it is not, if it not have any trivial, it is a common attribute, then we can say that it is not a trivial function dependency. Okay, so here you can say if you take the intersection of alpha and beta, here you will get D, and here also here you will get B. If you see the other options, there is no common attribute between this function dependency set. Okay, so the correct option is answer 4, option 4. Okay.
Yeah.
Any questions? Okay. If no other question, we can wind up now.
I said we
Yeah,
have
yeah,
some.
sure. Yeah, Kumar.
Ma'am, we have some other question. I want to just discuss for 5 minutes.
It's about the ER diagram, right?
Yes.
Okay. So the others who are, if you're interested, you can stay back. Otherwise, Kumar has to discuss something about ER diagram. Kumar, we'll just take it for 5 minutes. Is that okay? We'll discuss it for 5 minutes. Is that okay?
Okay.
Would that be enough, or would you need more time?
I had a couple of doubts from activity 5.2, if we can do.
Okay. Just 1 second. What is that activity 5.4?
I think we can first take the activity questions. Yeah.
Okay. So the question that Kumar had is with respect to the week 4 content. Kumar, can you do me a favor? Can you just post that in the Discord? Shall we discuss it there, or do you want to? Would that help?
I'm putting the chat link.
Okay. No. Actually, exact the question statement. That's also what.
So the thing is, ma'am. So once after opening that, there is a that one row is there. I have written it has the 5 attribute.
Okay.
And the email ID, group ID, and house name, city and state. So group ID house is the 12 houses, and every house has that 1 to 30 group ID name, and name is the 1 to 30.
Okay.
So there is a 12. So there is a many group ID. One house can be 1 to 30. So the group ID can be many. And second one is the city and state. So in the one state there can be many city. So there is a possible many city has the one state. So I want to, so in that all the thing was given in the 5 row, the 5 column. So I want to make it table. So what happened? I just created a thing is here from my knowledge, the one ER diagram. So want to discuss this ER diagram is correct, and if it is correct, then how to convert in the table.
Okay, we got the question. Okay, so what we'll do is we'll take it offline, I think. Okay, or we will see it on the practice, because first of all, we have questions on the activity questions of week 5. I totally understand this is a practical scenario that you want to discuss and you want to figure it out. I remember you posing the same question last week also. So can you just draw it? I mean, update it in the. I add it as a question, the discussion forum, and then can we give you inputs there, detailed inputs there?
Okay.
Just add a snapshot of this ER diagram and we will try to get back.
Yeah.
Okay.
Yeah.
And if you have any further doubt after that, I think, ma'am, we can have a breakout session in the next session.
Yes, sure. I think we may need one extra session or something this week. I'm not sure, depending on how difficult are the concepts in this week. So we can address it at that point also.
I also want to discuss on that, ma'am, that so suppose I make some table, and so is that table is sufficient, or that it is the further can be break in the best possibility, or that much is enough? So about the
that kind of decisions, I think we should wait for maybe another 1 week. After we learn the normalization, you will be able to conclude whether it is the best scenario possible. So there is a trade-off between, decomposing it to a finer state and then and then it versus the time required to access the data using multiple joins. Okay, you can decompose into multiple relations, and you can go to the finest refinement. Problem is what happens during the retrieval of data when you have to again have a join to combine all these tables together. Join is an expensive operation. So these kind of things it will become more clear when you learn about the normalization and all those things in the next week. So I would say that you can save that particular kind of doubt, right? Whether that is optimal relation, I mean, breakdown or something. Okay, you can never say when there is a decomposition is optimal. It again depends on what trade-off you want to go for. But even with whatever limited information you have, if you want to decide whether something is optimal, I would say that you can actually wait for one more week before you. Of course, we can work on your doubt. You can pose the question, but to decide whether that's an optimal decomposition, something I would say you can wait till next week.
Okay, sure.
The normalization, denormalization, right? When you do some normalization. So all these conditions, the 1NF, 2NF, everything that's going to come, these things have their own importance. Okay, their own. What do you say? Why are we decomposing it further and further refining? That is required to remove redundancy and lots of things. But at the same time, there is a trade-off, which is like you will have to combine multiple tables to retrieve the data. And because join is an expensive operation, how much of a refinement do you want to go is a choice that you will have to make. So you cannot say that there is some decomposition which is the most ideal. It depends on your scenario and all this. So maybe that kind of a thought process, I think you will be able to make a better decision on those things in after next week's lectures.
Okay. I'm getting most of it now. Slightly, I'm getting more into that and able to decompose and understand properly. Now, want to know that what's happened like that in this particular question. Last session, Arup sir told that you can break in the one to many type of thing, and I did. Then I realized that there is a relation between like the city and as well as the group ID. Also, there is a relation. So how to handle that?
You please that figure what you have drawn, no? You please post it along with a small description like what you want. I'll try to answer it today only.
Okay, sir.
Okay, then we can have a discussion over there itself.
Okay.
But as Dhanya ma'am told, like things will be clear like when you have completed next week content. Like we can do it, but we cannot prove it. It's the optimal right now. It's just like an idea we have. Okay, we can say it's okay or it is not good. But the proof, like it's really optimal, that we can do next week. That's the point.
Okay. Once we are able to make a table, that much is also enough, right?
Yeah, that's fine. That's fine. I'll answer.
Okay.
Yeah, Bimlesh, you had some doubt in activity 5.4, is it?
5.2, ma'am.
5.2, yeah, please ask.
The first question in 5.
Yeah.
Option B, why it is correct? How, I mean?
SID determines S joining date, is it?
Yes, ma'am.
Yeah.
I mean, on the principle many to one, it looks fine, but joining date could be different. It's just like it's kind of primary key. It's acting SID here.
SID is not the primary key, but see, if S001 has the joining date 23/6/2001, then S001 cannot have any other date. Cannot. Okay, one second. Let me just take the answer.
No, it's correct.
Yeah, correct. So, Piyush, do you want to share that? Do you have that? Just one second. I can also share.
Yes, ma'am. 1 minute.
No, I have it open. 1 second.
I mean, joining date could.
Yeah.
It's kind of like joining date of a particular session, and different students can have different joining dates as well.
That is okay, but all of them have joined on the same date. That's all. So I didn't understand. Okay. See, choose the functional dependencies applicable to the given table means that the given instance. From the given instance, what are the functional dependencies that we can conclude? That's all what we are saying.
Okay, based on the given records.
Yes.
It's not like I mean, it's
See,
one doesn't need to assume that the joining date could be
you
different.
can never
also.
assume anything because the use cases are totally unimaginable in the sense that we cannot even imagine what kind of scenario will be there with respect to use cases. So with respect to the given instance, what are the applicable functional dependencies is the question.
Okay. And question 5, ma'am.
So never assume any dependencies. Okay. So this is something we frequently see in the discussion forum also. People say, why wouldn't if there is a course ID and enrollment ID or a course ID student ID enrollment combination, I saw one post. Why would you assume that the student can enroll in multiple courses? The relation schema that is given says that the student ID is the primary key in a particular table. Say student ID, course ID, and some enrollment date. And it is said that the student ID is the primary key. So that is the use case. It means that the student can register only for one course. So that's a use case. You don't have to assume that no student can register for multiple courses. So it very much depends on what is the schema given to you, what is the instance given to you. So here there is no schema given. So functional dependency you have to conclude based on the given date instance. That's it.
Okay. And question 5, why option C is wrong?
A table may be such that there can be no super keys. Yeah.
I mean, suppose it's a weak relation there.
Yeah, it may not have, what is it? It may not have primary key, but it must have candidate key because it should be able to uniquely identify every tuple, right? In a table, it should be able to uniquely identify every tuple, no?
Suppose a table is a weak relation. As such,
Weak
I mean, there is
entity,
no
weak entity, corresponding to a weak entity.
Yes. So in that case,
Himalis, we should have a discriminator, right? That identifying set of attributes, right?
Yes.
Even for the weak entity.
That should be the candidate key for that. No? I'm sorry, the super key,
right?
Yeah.
Okay. So a discriminator is a super key in that case.
Yeah.
Okay. Okay. Thank you. And Mr. Arup, from the previous session, you had told that you will be continuing regarding the notations of VR diagram in some next session.
Yeah, I'll continue that. Today, do you want it to be done? Like today we are already running late, or?
I mean, just wanted to remind you, we can do it next session.
Yeah, next session.
Thanks, Vimlesh, for reminding. Yeah, but we will take it up maybe next session, or maybe we can have another separate session also, because the week 5 content is a bit tricky, as you can already see that. So we can have maybe an extra session if you are all okay. We will see.
Yeah, but that if that can be done before quiz 1.
No, what we were talking
quiz
about.
Quiz 1 is from week 1 to week 4.
Okay. You want
on Thursday, is there any session after DBMS session, or that is the last session? For the
Thursday there is, I mean, as far as AppDev is not there, I'm sure. I don't know.
We are having from 5 to 7.
Yeah, we can
if
continue.
There is no more session, I'll continue. Yeah.
Okay, there is no more session after 7.
Okay, then I'll continue on Thursday.
Okay, thank you.
Yeah. Okay then. Thank you, everyone. I hope there is, I mean, are there any more questions on the activities, the AQ questions anymore in the week 5?
We will get that in the practice session, I think.
Okay, fine, sure. Okay then. Okay then, thank you everyone for joining. Okay.
Thank you.
Okay, thank you.
Bye-bye.
Thank you, ma'am.